Section 4.3 is about multiplying matrices, not just multiplying them by a scalar that we learned in Section 4.2, but now we're going to multiply two matrices together. The key to doing this is that you can multiply two matrices if and only if the number of columns in the first is equal to the number of rows in the second. So here's what I'm saying. I have an A matrix and a B matrix, and the A is a 2 by 3, so it has 3 columns. And the B is a 3 by 4, so it has 3 rows. If the column and the row are the same, then you can multiply them. And what you'll get is you'll get a matrix in the end that's a 2 by 4. So if you write your two matrices next to each other, their dimensions, so here's the first dimension, here's the second dimension. If you write them out and the inside number is the same, then you can multiply them, and what you'll get is a matrix that's made up of the outside numbers. So let's look at an example. Determine whether each matrix is defined. If so, state its dimensions. So matrix A, we're told, is a 2 by 5 matrix. And matrix B is a 5 by 4. Well, notice the inside values are the same. The column and the row of the two matrices is the same, which means if I multiply them, what size will my matrix be? It'll be a 2 by 4. So I can say, yes, these can be multiplied and I'll get a 2 by 4. How about over here? 3 in the column and 4 in the row. So no, I cannot multiply those two matrices because they don't have the column and the row matching up. Here we're going to look at how to multiply matrices, and this can sometimes be difficult. The pattern is sort of a complicated one. I'm going to try to explain it to you. Basically, it's saying that the first element of an array that you get as a solution, I should say, the first element is made up by adding together, taking the sum, of the products of the first row and the first column in the arrays that you multiply. So in this example, I'm going to take row 1 and I'm going to take column 1 of the second matrix. I'm going to multiply them and add those two numbers together. Now that's kind of complicated and wordy, so let's take a look at an example and see how it works. So I want to find RS. And the first question we have to ask is that even legal? Well, we have matrix R is a 2 by 2. Matrix S is a 2 by 2. So the column and the row match up, which means my solution matrix will be a 2 by 2. So yes, I can multiply them together. Now, how do we do it? The first thing we do is we multiply the first row by the first column, and we add those solutions up. I'm going to take row 1, which has a 2, and multiply it by the first element in column 1, which has a 3. And then I'm going to add that to the second element, negative 1, times the second element in the column of a 5. Now I'm going to multiply the first row by the second column. So up here I'm going to do the 2 times the negative 9, and I'm always going to add that to the negative 1 times the 7. Now I'm going to take the second row and multiply that by the first column. So the 3 gets multiplied by the 3, and the 4 gets multiplied by the 5. And the last element is created by multiplying the second row by the second column. So 3 times negative 9 plus 4 times 7. And I'm going to simplify each one of these. 2 times 3 is 6. Minus 5 will be 1. Negative 18 minus 7 will be negative 25. 9 plus 20 will give me a 29, and negative 27 plus 28 will give me a positive 1. So R times S is this matrix. Here's an example of a problem we can solve if we create matrices and then multiply them. We're given some places for some schools in a track meet. We're told that teams are awarded 5 points for first place, 3 points for second, and 1 point for third. So I'm going to have a matrix for the results, and I'm going to call that matrix R, and it's going to be made up of these numbers over here. And then I'm also going to create a matrix for the points that are awarded, and it's going to be made up of the 5, the 3, and the 1. Now there's a reason I made this a column matrix and not a row matrix. And the reason is because this one is a 4 by 3, and if I multiply that by a 3 by 1, I'll end up getting a 4 by 1 matrix from the multiplication that happens. And that's what I want to do. I'm going to take this results matrix and multiply it by the points matrix and get a result. So I'll start by multiplying the first row by the first column. So 8 times 5 plus 4 times 3 plus 5 times 1. Remember, we multiply the row by the column. Now we'll do second row. 6 times 5 plus 3 times 3 and plus 7 times 1. And then you can finish this with the third and the fourth row. So that's what it would look like if I multiply each row by each column and added them together. And so let's see what the solutions are. So these would be the 4 solutions, or the 4 results. It looks like 57 is the winner. So if we go up to our table, we notice the top one is Jefferson, and they won. Here's an example of multiplying matrices. I want to demonstrate to you the commutative property. We're going to start by multiplying P times Q. Now P is a 3 by 2 matrix, and Q is a 2 by 3 matrix. So we know we can multiply them, and we know we're going to get as an answer a 3 by 3. So we're going to multiply the first row by the first column, the second column, the third column. I'm going to leave it up to you to multiply those out longhand. I'm just going to write the solution out here. And now we're going to look at what happens if we do Q times P. So we do it in the other order. So Q is a 2 by 3 matrix, and P is a 3 by 2 matrix. So we can multiply them, and our solution will be a 2 by 2. Again, I'm going to let you multiply rows and columns in the order, and here I'll just write the solution again. So what I'm trying to demonstrate to you is that the commutative property does not hold for matrices, which means that when you multiply matrices, it's not commutative. You don't get the same answer like you would if you were multiplying 3 times 2 or 2 times 3. Now that leads us to this last concept summary, which tells you that there are some properties that do hold for matrix multiplication. You can multiply matrices using the associative property. You can do it for matrices and scalars. And you can do left distributing and right distributing for matrices.